Right. So in the first part of this lecture, or in this chapter, we have seen how DAC is working and the analog comparators and the registers related to that. And then we have talked about ADC in general, their major characteristics like the offset, what is it, the span, how we do the calculation for the resolution and the weights and the conversion time of analog to digital conversion. Then we solved a couple of examples related to those. And also we have talked about one of the ADC technique, which is successive approximation, and this is what we are using in ATmega 128 as well. And we have shown how we can do a calculation using successive approximation. And then we touched a little bit on the linear sensors, and we have said that there's a linear relationship between the measurement and the voltage, and we have solved an example related to that as well. And also we talked about signal conditioning, because it requires to convert to valid logic voltage levels before we perform any analog to digital conversion. That's why we require signal conditioning. And at the end of the first part, we mentioned discrete ADC components. So if we don't have an ADC module on our embedded system in our microcontroller, we can use discrete components, which they are available on the market. And we have seen an example, which is an 8-bit ADC, which is similar to the ATmega one, and so on. So now we are going to get into the ATmega side of analog to digital conversion, which is offered to us. And you can find all the details of this in the data sheet as well, but I have to highlight some of the important points and metrics to interface ATmega with the sensors and so on. So the first thing, the characteristics or the properties of ADC in ATmega that we are going to use. It is a 10-bit analog to digital converter. It has got 8 analog input channels and 7 differential input channels, and 2 differential input channels with optional gain of 10 or 200. Normally, the converted output binary data is held by 2 special function registers. So we have got this data register actually, but it's ADCL, which is the analog to digital conversion low, and ADCH, which is analog to digital conversion high. So we can store the low bytes and the high bytes in 16-bit register that we can create. So the only thing that we need to be careful over here, as it offers us a 16 bits, but our ADC is 10-bit, we have 6 unused bits on the registers. So we can configure this ADCH and ADCL to be either left justified or right justified, which we are going to see that in the following section. And we also have 3 options for the reference voltage. It can be either connected to analog voltage source, VCC, or it can be connected to internal, which is 2.56 volts reference voltage, or it can be an external AREF pin that we can use for it. And generally, the conversion time is dictated by the crystal frequency connected to the X-stall pins, and it can be configured with ADPS bits in the register. So we have got 2 modes in ATmega for ADC. One of them is the free running, another one is the single conversion mode, which we are going to see those as well. And also we can use interrupts with the analog to digital converter. So whenever the conversion is complete, it can raise a flag and says, okay, I'm done with the conversion. And also the good thing about ATmega's ADC, it has got its own ADC noise canceller. So we can use this noise canceller to have a maximum accuracy on analog to digital conversion. So let's get into the AVR now, and let's analyze these properties in details. So ADC power and signal delivery, this is the part of ATmega's pins, which represents the analog to digital conversion pins, so analog pins that we have got in port F. And this is the internal circuitry of it. It has got its own low pass filter for each of these pins, and this allows us to keep the digital noise outside of the analog to digital conversion. And we can use over there analog voltage source, so we can have an extra filter for the circuitry, and we can use the decoupling capacitors to avoid any noise over there, and we can actually have a more stable voltage reference, so this will give us high precision in ADC. And important things that we need to keep the analog signal path short and reference to ground plane, and we can also use the ADC noise canceller. So what is ADC noise canceller? In ADC we can use a couple of register to modify or power down the CPU. So as we are powering down the CPU, we are actually reducing the digital noise as we are doing the conversion. So whenever the conversion is done, we can wake up the CPU and we can process the converted data. And that's why interrupts are really important in every part of this embedded systems. So in ATmega or AVR, we have got the control registers that we can modify and update, and we can use it in sleep modes, and we can reduce the noise over there. So I hope these are clear. If you don't have any questions, please do not hesitate to ask me during the question and answer session. So the next thing that we are going to see is the structure of the ADC. So this is the ADC module inside of an ATmega. I'm just going to go and zoom in a little bit because we need to analyze this in details now, so that we can understand what's going on with each of these modules. So let's start with the ADC multiplexer, which is known as ADmax. So inside of the ADmax, we have got 8 bits for the configuration. So in these 8 bits, we have got the first most significant bit, refs, one and 0, which is bit 6 and 7. So these are known as reference bits. What are those reference selections? So when you want to select the reference voltage, which they are directly going down to the internal circuitry of or the external sources, we can either choose the AREF pin or AVCC pin, or we can just use the internal 2.56 volt reference voltage. So refs are organized as follows. So if you want for 00, it's a ref. For 01, it's a VCC. And 10 is not used, and 11 is internal. And this allows us to select what kind of reference voltage we are going to use. So please consider that if you want to connect the VREF pin to an external fixed voltage, you will not be able to use the other reference voltage options in the application. as they will be shorted with the external voltage. So we have to be careful over there. And if you want to connect a 100 nanofarad external capacitor between the VREF pin and the ground, this will increase the precision and stability of the analog to digital conversion, especially if you want to use an internal 2.56 volts reference. So these are related with the decoupling of AVCC and the ref pins. The next thing that we are seeing is the ADLAR. So ADLAR is another bit in the register ADmax, which is bit 5. So ADLAR, as we already said with the properties of the ATmega, this is bit 5, and this is actually adjusting the results. So as we have got two registers to store analog to digital converted data, we have got ADCH and ADCL, and this is representing the high byte and the other one represents the low byte. So as we already said, the ADC, in this case we have got 16-bit output, but ADC is giving us only 10-bit output. What we can have is, when ADLAR so for ADCH and ADCL we have got for high byte and the low byte. What we can do actually, ADLR, when it is 1, we can say that our D9 to D2 will be on the ADCH and D1 and D0 on the ADCL, and the rest is unused. Or if we say ADLAR to be 0, in this case we are right justify the results. So this will be the unused part. In that case we have got D9 and D8 over here, and the rest of the bits on the other side. So D7 to D0 will be over here. So ADLAR bit is actually telling us if it's going to be left or right justified for the data. Then we have got max 4 down to 0 bits. So max 4 down to 0 bits, it represents the analog channel and the gain selection for it. So this is actually going in to the max decoder down to the analog channel, and it also specifies the gain for the amplifier if we are using differential inputs over there. So max decoder, based on the 5 bits, if you want to have a differential one, this also specifies the gain amplifier, the gain itself, and it also selects which combination of analog inputs are connected to ADC on this part. Then we have got ADC input channel over here. which are connected to port F, and we can use this to select either the single end or the differential input to convert it to digital. If we selected single-ended input, we just choose AD7 down to 0. But if you want to select the differential input, we can also select the op-amp gain over there. So that's the input part of the ADC. Then we have got status and the control register, which is an important register, and we need to use this register to control and monitor the operation of the analog to digital conversion. So the first bit, which is ADN bit, it enables ADC. So if it is 1, enable. If it is 0, disable. Then we have got ADSC bit. ADSC bit, we need this bit for the conversion because this actually starts the conversion. So we have to set the ADCS pin to start the conversion, and the important thing about it, if it's in the single mode, this has to be always set to 1 until it finishes the conversion, then it goes back to 0. So during the conversion it's 1. Then we have got ADFR. ADFR bit, it's actually the free running mode. So in ADC we have got 2 modes for conversion, either single conversion mode or the free running mode. So if you want to configure it in free running mode, we have to set that pin to be 1. And as we already said, ADC has got interrupt, so we have got ADC interrupt flag. So if the interrupt is enabled, whenever the conversion is done, interrupt flag will be erased. And to have an interrupt, we need to have interrupt enabled to be 1 set, and this is interrupt enable. So IDF is over there and enable is over there, and then we can enable the interrupts. If you want to use interrupts, we can also use polling methods over there. And then we have got ADPS bits. So ADPS 2 down to 0. This is actually for the prescaler. The ADC, actually the approximation that we have defined in the previous section, it requires the clock. So ADC actually requires a clock to make a conversion. And generally, the clock has to be between 50 kilohertz to 200 kilohertz. And as our system clock is generally 10 megahertz or 8 megahertz or 16 megahertz, we have to prescale it down to 200 kilohertz, less than 200 kilohertz, to have the best accuracy. So to do that, we need these scalers, and it used to determine the division factor between the clock and the input clock of the ADC. So it can be configured 2, 4, 8, 16, 32, 64 or 128. And we'll see these bits later on as well. So as I said, ADC requires a input clock less than 200 kilohertz for the maximum accuracy. That's why we need to use prescaler. and that prescaler goes into the conversion part. So these are the most important part of the ADC that we are going to use generally. And before we carry on, I just want to show you why 200, why do we need a prescaler. So for example, if we have got 8 megahertz clock, so with the 8 megahertz clock, if we configure ADPS pins down to 0 to be 001, this will give us the clock divided by 2. So that means 8 megahertz divided by 2 will give us 4 megahertz. And as we know that we need less than 200 kilohertz, so 4 megahertz is greater than 200 kilohertz. This is not valid prescaling. Let's try another one. Let's say we have got ADPS 2 down to 0, which is 100, and this will give us clock divided by 16. So 8 megahertz divided by 16 will actually give us 500 kilohertz. Still, it's not valid because 500 kilohertz is greater than 200 kilohertz. So we cannot use that prescaling. Then we can try another one, ADPS 2 down to 0, which is 111. On the other hand, if you don't mind about the conversion times, what you can do is, for the best accuracy, just set it to 111, which will give us the highest prescaling, so 128. And this is going to be 8 megahertz divided by 128, which will give us 62 kilohertz. So that is less than 200 kilohertz, and it's valid for ADC clocking. Another thing that I want to mention about the clockings and the prescalings and so on, in ADC we have got a sample and hold time. So sample and hold time, it actually samples and hold it and convert it and so on. And acquisition time is the timing factor that we should know about. So we can say that, maybe for the next slide. So this is the multiplexer selection, which we already done. So this is the prescaling part. So after an ADC channel is selected, the analog to digital converter allows us some time for the sample and hold capacitor to charge fully to the input voltage level present at that channel. So this is why in the AVR, first conversion takes around 25 ADC clock cycles in order to initialize the analog circuitry and pass the sample and hold time. Then each consecutive ones are going to be 13 ADC clock cycles. So once again, when we want to start analog to digital conversion, for the sample and hold capacitor, it has to be charged fully to the valid input voltage level, which is presented at that channel, and that's why we need an extra 25 clock cycles in order to initialize this analog channel. Then the rest of the consecutive conversions will be 13 ADC clock cycles. And once again, if the conversion time is not critical, we can just set the prescale to be 1111, and we get the maximum accuracy over there. So I hope these are all clear, because they are really important and we need to understand this to configure AVR when we want to program it. And as we already said about the ADLAR bit, so we can either choose a left justified or the right justified for the data coming in, as we have got 10-bit data. Or maybe what you can do, you can just do a left justify. We can just use the 8 bits of it, which will be enough in some cases. And we can just read the high byte of the converted data, and we can throw away the 2 bits that we have. And this is actually how it is represented with the registers itself. Now, as we already said about the AVC has got 2 conversion modes. This is the single mode, and the other one is the different free running mode. So again, we can say that we said that we can set the free running mode with the bit 5. Now with the free running, the single mode, what we need to do, we have to first set ADSC, so start conversion bit, to be 1, and we have to keep it 1 until the end of the conversion. So then this will be actually cleared by the hardware when the conversion is completed, so we don't need to do anything in the software side. When we raise this, it will start the conversion. After the conversion is done, it will fall down, and then the next conversion, it will go back up and carry on. And also, if you want to change the channel, but it's performing a conversion at that time, it has to wait to finish the conversion first, then it will change the channel. Or if you want to change the reference voltage, it has to finish the conversion first. So how do we do the ADC completion? Generally, we have 2 methods. Either we poll and check the interrupt flag, or we just wait for the interrupt flag if we set the interrupt flag enable, so that ISR can clear the flag and goes back to the normal conditions. And this can be seen from here, that interrupt flag is coming in after the 13th cycle. Then it puts the data on the ADCH and ADCL. So if we are in the free running mode, it's actually, we can set it with the ADFR, as we already said. It starts the conversion and it can perform consecutive conversions without checking the flag. So it keeps converting and converting and converting without checking the flag, and it says generally the first conversion is longer than the rest. So these are the 2 modes that we have got in ADC. Now, as we are going to get into the programming side of ATmega for analog to digital conversion, there are various steps that we need to take care. So for the setup, we need to have a reference voltage, so that's why we generally use AVCC pin to supply a analog voltage over there. Then select the input channel via the input multiplexer, whatever the channel we are going to use, single end or the differential one, we have to select that one. If we are going to use the interrupts, we have to enable the interrupts, and we have to enable the analog to digital conversion. So the reference voltage actually determines the maximum and the smallest voltage for the ADC, and in ATmega case we normally use AVCC as 5 volts as a reference, so that means it should not exceed 5 volts because of the electrical reasons, and in this case input voltage resolution is 5 over 1024. 1024 comes from 10-bit resolution, so this will give us 4.88 millivolts. And for 0 volts, it's going to be hex 00 ADC output, and for 5 volts, it's going to be hex 3FF. Now, the steps that we need to do to program ATmega while we are doing a programming. First of all, we have to make or select or set the port to be an input port. This should be in the port F. It can be either individual pin or a complete port. We need to set it to be an input. Then we have to turn on the ADC, so we have to configure the ADC registers, the control registers and the max. So depending on the clock that we are using, 8 or 10 or 16 megahertz, we need to pre-scale it down so that ADC has a clock which is less than 200 kilohertz. So we can select the conversion speed, and then we have to select the voltage reference that we are going to use. Again, this is depending on the sensors that we are using over there, which we are going to do an example in a minute. So we have to decide for the reference voltage, internal, the AVCC pin or the reference pin. Once we have set it up, all the registers related with the analog to digital conversion, we have to activate the analog to digital conversion or start the analog to digital conversion by setting ADSC pin. Once ADSC pin is set, it runs for 13 cycles if it's not the first one. If it's the first one, it has to be 25 cycles. Then it sets the interrupt flag. If the interrupt is enabled, it sets. Otherwise, we have to pull it and check it if it's set or not, because in the end it says that the conversion is done and the digital data is ready. And once the digital data is ready, it's stored in ADCH, the high byte, and the ADCL for the low bytes, and we can get the data from there to process it. So if we want to read more data, we just go back and start again from the conversion side. Or if you want to change the channel and read a different channel or change the reference voltage, we have to wait the conversion to be completed, and then we can change those. So these are the steps that we are going to follow when we do the programming of AVR. So here is our first example. It says LM34 produces a voltage output that is linearly proportional to the temperature with 10 millivolt Fahrenheit resolution. The range is 50 Fahrenheit to 300 Fahrenheit. Determine the VREF to be used for analog to digital conversion. Now, the range is given to us. So the range is minus 50 Fahrenheit to 300 Fahrenheit, and we have got 10 millivolt as the resolution for the sensor. Now, for the ADC, we have to go through and check if the values given will be fit, or we have to decrease the resolution. So to do that, let's start with 10-bit resolution, which is the highest resolution for ATmega's ADC. So for 10-bit resolution, we need to have 2 to the power 10 and 124. Then that has to be multiplied by 10 millivolts per Fahrenheit decrease, and this will end up at 10.24. Now, this voltage range outside of the sensor range, and it's actually outside of the analog to digital range with any of the ATmega 128 reference pins. So we cannot use 10-bit resolution. Let's check 9-bit. So for 9-bit, we need to have 2 to the power 9, which is 512 by 10 millivolts per degrees Fahrenheit, and this will give us 5.12 volts. Again, this is out of the range. It's bigger than the 5 volts, larger than the 5 volts. Then we can try 8-bit resolution. So for 8-bit resolution, we will have 256 by 10 millivolts per degrees Fahrenheit, which will give us 2.15 256 volts. So this voltage is now enough for the ADC conversion, and actually it's similar to the internal VREF. So we can use internal VREF as a reference voltage for this question. The next thing that we need to consider in the question, let's write an assembly program to sense the temperature using polling and output the digital value using port D, and write a C program for the same. So our clock is 16 megahertz. So for the 16 megahertz clock, again, we need to have an ADC clock less than 200 kilohertz. That means we need to pre-scale this clock. The best resolution we are going to get from the dividing it by 128, which is 111 in ADSPA. So 16 megahertz, when it is divided by 128, this will give us 125 kilohertz frequency for ADC, which will be enough, and we'll get a good resolution, the accuracy for analog to digital conversion. So now we are ready to write the code for assembly and the C for ATmega. Right, let's start with the assembly program. The first thing to do is to set the port's input or output. Now, as port D is going to be an output port and port F is going to be an input port, let's define those. So LDI R16, it's going to be 0 hex FF. So out DDRD, it's going to be R16, and that's going to be port D and output. Then repeat the same thing for port F, but this time it's going to be 0 hex 00 and out DDRF R16. And we made port F an input port. Now the ports are ready. Then we have to define the analog to digital conversion register values. So I have to go back to ADC-SRA. In this one, we need analog to digital enable bit to be 1 because we have to enable the conversion. The start bit has to be set later on, so we have to put that to 0 now. ADFR, we are not going to use free running mode, we are going to use a single ended. Interrupt flag, this is going to be the polling, so we are not going to use interrupt flags, and interrupt enable is going to be 0. So the first 4 bits is going to be 1 0 0 0. That means LDI R16 100 is 8, so 0 hex 8, and then interrupt enable is 0. ADPS2 1 and 0 bits, we have to set that based on the prescaling. So for the prescaling, as we already calculated, for 16 megahertz we need to prescale it to 128, which is 111, to have the best precision over there. That means that's going to be 1111. So 0111 will give us 7, and that is going to be sent to the ADC SRA R16. So we can say that we enable ADC and select clock divided by 128 prescaling. So next we need to set the other register, which is AD max. So LDI R16 AD max, we have to go for this one. So refs is going to be 256, so 2.56 for the internal reference voltage, so that's going to be 1 1. So these are going to be 1 1. ADLAR, as it's going to be an 8-bit, let's just keep everything on the left justified, so we can store the bits into the high byte, and that's going to be 1 as well, so 1 1 1. Then max 4 to 0, we are going to use single end channel, so we can use the first channel and we can set it everything to 0 over there. So 1 1 1, and the rest is 0, which actually going to give us E0 in that case, and that has to be output AD max R16, and this will set at setup VREF 2.56 volt VREF, and ADC 0 single-ended and left justified. So we have got all the settings necessary for the analog to digital conversion. Next thing to do, we have to start the conversion. To start the conversion, we have to set the ADSC pin to be 1. So let's say start ADC. So when we start ADC, what we do, we can set bit immediate of ADSR CA of ADSC bit. So we can start conversion. Then what we do, we have to wait for the conversion to be done. So we have to check the interrupt flag. Because we didn't set the interrupt flag, we have to wait by polling. So polling, it's going to check SPIS if bit is set for ADC SRA, which bit? ADIF bit. So interrupt flag bit has to be checked. Is it the end of conversion? Then if it's not, go back to polling. So keep polling. Then if it's the end of it, what we can do, we can clear the interrupt flag. So how do we clear? We can set the interrupt flag to be cleared with set bit immediate, and then we have to get the value into a GPIO register. So in R16, as this is a ADCH is a part of the IO register, we can use in instruction over there. So ADCH is holding our 8 most significant bit, and once we got that in, we can just send it to port D. So send it to port D, and once we are done, we can go back with an R jump to start ADC. So this is just showing the assembly version for the polling of ADC. We can set up, enable the analog to digital conversion. We start the conversion, then we wait for the polling or the interrupt flag. When it is converted, we can just copy the value into the GPIO and send it to port D. And let's do the same thing for the C side. So we'll start with int main void parenthesis. So let's start with DDRD, which is equals 0xFF. Then DDRF equals 0x00. Then ADCSRA is going to be 0x87 for the values that we already calculated. ADmax it's going to be 0xe0, and that's done. So we have to start the conversion. While one ADCSRA can say set ADSC bit ADCSRA start conversion, and we have to wait for the conversion to be done. We can say while ADCSRA and interrupt flag is not set, so it's equals 0. Wait, then we can set ADSRA interrupt flag to be cleared. Clear EIF. Once it's cleared, we can send value to port D of ADCH and the bracket. So that's the C version of the reading a temperature sensor LM34. And there's one more example. It says write an assembly program to read analog signal through channel 0, convert it to 10-bit digital, and send it to port B and port D using interrupts. So the frequency is not given. Let us assume it as 16 megahertz again, so we can use a prescale 128 to achieve less than 200 kilohertz. We have to enable the ADEM bit. ADCSC will be enabled later on. We are not going to use the mode. Interrupt flag has to be enabled, so interrupt has to be enabled, and ADPS210 is going to be 111. So that has to be 1 0 0 0. That will give us 8, and 1 1 1 1. It's 8F actually. So ADCSRA is going to be set with 8F. For the max, we can again use the internal one as it's not specified. So we can set that to 1 1. ADLAR It can be left justified or the right justified. You can decide on that. And for the max, you can use the channel 0, so it's going to be 0, 0, 0. The important thing in this example is, as we are going to use interrupt, we have to look for ADC interrupt vector, which is 2A. So at the beginning of our code, we have to write that interrupt vector, so that from that vector we can jump to interrupt service routine. Let's see the code. So the vector for ADC conversion is given and defined for interrupt service routine. Then we start. So we set DDR B and D to be an output port, as it says, for the 10-bit digital value. And then DDRF is an input port because we want to read the analog data from the port F. So 8F for ADC SRA, which we already calculated, is used. And then AD max is C0, so 2.56 for VREF, and ADC 0 single-ended, and it's going to be write justified. So everything will be write justified. There will be 6 unused bits on the most significant bits. So then what we do, we start the conversion by setting the ADSC bit, and we wait for the interrupt. Then whenever the conversion is done, interrupt service routine will act, and it will store R16 ADSL value first. So that means the low byte first, and then send it to the port D. Then we read the high byte, and that will be sent it to port B. So we are reading byte by byte and send it to the output. And once we are done, reset the ADSC pin to start to the NIV conversion. So that's all you need to know about analog to digital conversion. I hope everything is clear. If you have any question, note it down and you can ask me during the QA sessions. Thank you very much.